around the country and residential buildings. We're now on the 2018 IECC. And Deb, I'm going to make a shameless plug for the next webinar that I'm going to do, which is going to be specifically looking at the 2018 IECC, which is the International Energy Code. And that's going to be coming up late this summer, early this fall, just to make sure that everybody's up to speed on some of the issues regarding that. There have been a number of changes made, particularly to the wind section of the building code. Some of this started in 2006, 2009, we saw a little bit of changing. And then as we move forward up to 2018, some pretty big changes. It really hasn't changed a lot of what we do, but it has the potential, particularly on the commercial side, to be a problem. So that's why I really want to make sure that we cover these things. There's a few other little changes that have been made with regard to drainage, and that's now been moved to the plumbing code, but you still got to have drainage on roofs. We've added a requirement for some of the wind testing. I have to remember which computer I'm on for the presentation. And some of this, I'm not going to go into a lot of details on that, but we are seeing blow-offs. And if we're seeing blow-offs on roofs, something's got to be done. It's not common to see roofs blow off starting in the middle of the roof, which is why this one was really kind of particularly interesting. And I've saved this slide for a number of years because what we found was nail placement was particularly an issue. And I'm going to pull in my mouse here. And let's see. Whoops, sorry about that. Let me go back. Need to, where's my mouse? There we go. And that's jumping on me. Here we go. Well, for some reason, it's not wanting me to do this. So we're going to go ahead and jump to the next one and we'll catch up. The biggest single problem I'm seeing right now with regard to wind is, what is the wind velocity? There was a big change that was made several years ago, and all the wind velocities in the country were raised. Well, really, there's two velocities that we use for wind, and they're basically equal numbers. However, they're called different things. We have the ultimate wind velocity, and when they really want to get confusing, they say the ultimate design velocity and the design velocity. And the relationship between these two is that the design velocity is equal to the ultimate velocity times conversion factor, which happens to be the square root of 0.6. We're not going to go into why that is. What's important here is when you are putting down winds velocities, if you have a design, if you're saying you meet something, you report the ultimate. If you're going to do calculations, you do them based on the design velocity, not the ultimate velocity. And if that sounds confusing, it absolutely has got some jurisdictions totally beside themselves. I have had to write 2 letters in the last 2 weeks, basically explaining just this one thing, because the building code official said we have to do 150-mile-an-hour wind. Well, but that's not the number that we designed to. That's your ultimate velocity. It's not what we're working to as a designer. So you have to report that this system can handle 150-mile-an-hour wind ultimate. If you're doing calculations, you have a lower value, which is the design value. Basically, anytime you have wind moving or air moving across a building, You have a reduction in the vertical component of the air pressure. That reduction in the vertical component of air pressure causes a net uplift as the air is pushing to get out of the building, and it pushes the roof off the building. And we see this very nicely with a commercial structure with something like this. But when we look at residential, we still have much the same thing. We have the push on the side of the building. We also have the wind going up and over, and as it does on the back side of the shingles, we'll actually get an uplift that occurs on this back side, which can pull the shingles off along the ridge. And actually, we have seen this in a couple of locations in the Denver area where, because of an escarpment and so forth, we had tile coming off of the back of a ridge, because as the wind goes up and over, it creates that negative pressure zone on the back side of the ridge and pops the tiles off. We can have actual tipping of buildings. That's not a very common effect in most markets, because we know how to anchor buildings and the weight of the building holds it down. But if you look at that the upper right-hand corner, and you get air inside of a building and you get the air going over the top of the building, now we get that lee side on the ridge and it will pop it off. The other thing that will happen is, if I have an overhang, I have the wind coming up from below because it hits the side of the building. Now we have a very large pressure gradient that can occur, which will push the shingles or tiles or whatever off from an eave or at the edge of the roof. So, very quickly, this is the table of the conversions, the design versus the ultimate. If the ultimate velocity is 110 miles an hour, the design velocity is 85. Now, I put them in as ultimates. This is actually taken right out of the tables we use for doing the calculations. This is from 1609, which is the structural chapter of the building code. And if you look, you can see we get 150 mile an hour ultimate wind. There's only 116 design value. Well, for most of the Denver market, we were using around 120 mile an hour wind. So we already were designing to 155 miles an hour ultimate. So when you start to see these huge numbers appearing, it's not as scary as it initially looks. It's just because of this shift in how we're supposed to be reporting it to meet up with what the requirements are of the building code. Now, there's other things that modify our uplift. If you have other buildings that are about the same height, it breaks up the wind. So we don't get that smooth laminar flow, which then hits the building, goes up and over. Everything is tumbling, and as the air is turbulent, we don't have as much uplift. And so that works to help reduce the effect. If the building is, the higher the building, the more uplift. I have some buildings that I've done some work on downtown that are 400 feet high. Once I get up to 400 feet, the wind velocities at the top, on a still day at the ground, we will have 20 mile an hour winds at the top. So the higher the building, the greater the velocities. The direction that the wind strikes the building makes a big difference. If it strikes it coming into a corner, we can do it this way. If the wind is coming and strikes the corner of the building, then the wind's going to come over the top and tumble, and that is going to create an enormous amount of uplift in the corner. And the newest thing, because we've only had wind around for 4 billion years, the newest thing is the fact that the code is finally recognized we live in Denver. And in Denver, we don't have as much air. Because we don't have as much air, we don't have as much air pressure, we don't have as much momentum in the air, and therefore, we now can actually reduce our uplift pressure because of the fact that we are at a greater elevation. So, just a very quick schematic of how the winds are greater in the corners and some of the uplift factors and so forth. How do we actually do the calculations? Well, it's a simple equation. The uplift is equal to 0.00256 K sub Z, K sub ZT, KD, V squared times the density, where K sub Z is a pressure coefficient, and there's a nice table of those. KZT is the topographical factor. That only really matters if you're at the top of a hill or there's an escarpment. Otherwise, it's a 1. Directionality factor is always 0.85. It's sort of like, why do we bother if it's always the same value? Why do we put it in? We just do. V squared is the design velocity squared, not the ultimate velocity. So you need to make sure, this is where it makes a big difference, because when you square something, a small change makes a big difference in the final outcome. And finally, there is the reduction for air density, and in the Denver market, that is 0.85. Now, I will tell you that there are some areas of wind design that have not really accounted for this. If you look at information on tile roofs, many of the codes have a requirement in there that you need so many fasteners for certain velocities. But with the reduction because of density, basically we can go to a higher velocity and still have the same amount of uplift. And this starts to become an issue as you move into the foothills, some places in Boulder particularly, where they have jacked the ultimate values way up. But in many cases, they didn't take into account the fact that we already have effectively some protection because there is a reduced density. So when you look at the code, and the code says for a tile roof, you have to do this type of fastening at this height and this wind velocity, those are based on sea level. When we get into elevation, we get into the mountains, now there really is, because of this air density change, we now can take advantage of that, and you can put tile roofs on at higher elevations from the ground and higher wind velocities, because you do have that extra cushion there. The ASCE 7 is the standard that engineers work from for determining loads. And in 2005, this was the wind speed map. And it's a great map, 90-mile-an-hour winds designed around the country. You notice there is, of course, a band of gray along the Front Range, and that's because we are special. That's special wind area. What happened is they changed the map. They went to 115-mile-an-hour wind. And a lot of jurisdictions jumped on this. They have a higher wind velocity. They did away with a few things. Number one, this is for Category 2 buildings. If I go back a slide, it doesn't say anything about category of building. What they used to do is have something called an importance factor. And if you had a barn or an ag building, the importance factor was less than 1. If you have a regular residence, the importance factor is 1. And if it's a special building, the importance factor is 1.15. And this worked really well, but they changed it. Now we have different maps depending on what category of building you have. Category 2 buildings, which is the vast majority of buildings, this is the map that we use. So I know you're all dying to use this equation. Let's do a little plug and chug. 0.00256 times 0.85 times 1 times 0.85 times the velocity, design velocity squared times the density. We can run these all out. And I know you're all sitting there plugging away on your calculators. So what's the difference? What happened in going from 90 miles an hour to 115 miles an hour? Well, here's the numbers. The field of the roof went from minus 33.35 pounds of uplift to 33.32 pounds of uplift. Not a significant change. The corner velocity, corner uplift went down 1/10 of a pound per square foot. But the velocity went up from 115, or from 90 to 115. Well, what was happening was we had to then reduce it. So now let's jump ahead. We have a new version of ASCE 7. We now have the 2016 version. And now if I plug in chug, I have an air density factor that I can take into account. Look at what's happened to our uplifts. A pretty significant reduction. That 15% reduction, because of the air density, makes a big difference in what we have to worry about as far as attachment goes. Now, I will tell some of you who've been clients for a long time and we've done calculations, there has been a footnote in a sub-appendix at the end of the book that I knew about, and I used the extra 15 sort of as a safety factor. Well, now the code says I kind of have to take that into account. So I lost a little bit of my safety factor there, but I'm still pretty comfortable with how we do things. This makes a difference in the Denver market. And so when we're working in Denver or higher, taking this into account can have a pretty significant difference in our fastening. Now, what was the other big news in the 2016 version of all this wind stuff? A lot of little teeny letters. Used to be we had corners and perimeters and field. Now we have all these 2 sub E, 3 sub E, 2 sub N, a lot of extra stuff. If you notice, we now have 2 bands of perimeter on a low slope roof. And each of them is 6/10 of the height of the building wide. So if you have a building that's 20 feet high, before you have any field in the middle, you've got 48 feet of width just in your perimeter. Well, wait a minute, the perimeters are now overlapping because the building's only 40 feet wide. Well, guess what? You're just doing the whole thing as perimeters. This is where you ask an engineer to help you out. I will tell you, as an engineer, there are definitely times that it is easier for me to just say fasten the whole thing like it's a perimeter, because fasteners are still relatively cheap. If you screw up in some dimension going in, is that worth a handful of fasteners? Large rectangular buildings, if they're long and narrow, you probably may have almost no field. If, on the other hand, it's a large square, then yeah, okay, there in the middle we can reduce our fastening a little bit. So just to kind of give you an idea. Now, for those of you who are saying, well, I don't want to do any of this, I want to go ballasted. Okay, let's go ballasted. I added the ultimate wind speeds on the top. The design wind speed is this is right out of the building code. The ultimate, if we have an ultimate velocity of, for example, 155 miles an hour, if the building is under 15 feet high and there are other buildings around it, you could potentially put a ballasted roof on. If it's out pretty much in the open, if you have 130 mile an hour ultimate velocity, your max height is 15 feet. So this gives you a little bit of an idea of, there's been a lot of pressure to kind of get rid of ballasted roofs. So this is not changed. However, what's happened is the design, the velocity stated in the building code is a design velocity. They demand that you report things based on an ultimate velocity. And here we see a lot of confusion. If my local code authority says I have to design for 155, there isn't a system out there on this table that lets me do that, because this only goes to 120. But that's a design value. So the code people require us to tell them the ultimate, but in the code, it doesn't list the ultimate. It just has the design. So that's another one of the little confusing things. Fastening, make sure you've got the right number and the right placement. And it's an engineering thing. I will tell you that the picture you're looking at is a job that was in litigation, and no, not even close. The positions are all wrong. The counts are all wrong. I actually cut this hole because the consultant that was opposing me said he didn't know where the fasteners were and therefore couldn't opine as to whether they were enough. So I opened the roof up and made him step into this section when he got off the ladder, and he couldn't deny that he could see the fasteners. So what happens if you screw up? Well, the roof blows off. Golden, you notice that the fasteners were all placed right at the edges. That's not where they go. You have too much bow, and if I fasten near the edge, as it bows up, it breaks the board. If I fasten in farther, then that other board acts sort of as a cantilever and helps to hold it in place. You have a less likelihood of blowing off. So all you residential guys out there, don't be too gleeful at the expense of your commercial contractors. Overdrive of fasteners just is become a real bugaboo for me and a lot of inspectors. The red marks indicate overdrives. They don't hold. So you've got to be careful. All right, we have a poll question. And I guess, Deb, we're going to do about a minute, I think, for this. Code official says the wind requirement is 155 miles an hour. Which of these is most likely true? 1, the roof will blow off. 2, the velocity is the ultimate, not the design. 3, only a heavy ballasted system can be used. It says I can't vote, so you're on your own. Yeah, when you see me looking down, I'm looking down at the same screen you're looking at on your machines. Debbie, that's probably long enough. If people are going to vote, they've got it voted. The answer is that's probably an ultimate. And it looks like most of you got it. So that's good. Yeah. The roof could blow off. All right. Let's just talk, and I'm going to go through these fairly quickly. A little bit on house movement. All houses move, some more than others. Denver, I swear in the last year I've seen, and I've had more people complain, oh, I've got You know, my house, my roofer was on the house, and now all of a sudden it's cracking and I've got problems all over the place. Some of it may be because of tile, some of it's because of heavyweight shingles. I would tell you that in a lot of cases, people think roof and they look up and they see a crack in their house. It's got to be the roof. I just had it roofed. Doesn't matter that it happens in a location that isn't connected to the roof. Or it doesn't matter that it was an addition that the foundation is settling. Everybody knows that it's the weight of the roof. And I will tell you, I had one I looked at yesterday where it was a roof I had looked at 6 years ago. Everything went smoothly. The homeowner calls me up and says, Rich, my whole patio's coming down. So we got out there and that much of a drop. Come to find out, when the builder built his patio, the post is here, the beam is here. He didn't put the beam on top of the post. Not a difficult fix, actually, but it's like, come on. When you get a complaint, always check it out. It could be a problem. So if you have a homeowner that says, I think this roof is causing a problem on my house, go take a look. Let the homeowner show you all the problems they're seeing. Make sure the crack isn't a cobweb, and I'm going to show you some pictures of that. It's amazing how often I get out to the house, there's a crack on the first floor. It's a 2-story house. I had one where it was a freestanding shower and the door to the shower wouldn't close. There was nothing on the top, and it was the weight of the roof that was causing the shower door to bind. Sometimes people come up with some weird ones. The other is, over time, if I have a large wood beam and a drywall ceiling, there's always going to be a crack at that interface. There are some in the Denver area that are real. This is one, I got a phone call. They said, Rich, how soon can you be in Wash Park? I said, about 2 days. They said, the house is collapsing now. I was there in about 15 minutes. Fortunately, the contractor was able to shore up the brick. The problem is, and we put out, CRA put out a warning on this, and whenever you're working in any of the old areas of Denver, they didn't put cross ties. So if I have a house that's built like this, I've got the ceiling joists holding it together. On a lot of these older houses, the ceiling joists were perpendicular to the rafters. So if I load the roof, the walls go out. So you want to be really very careful, especially on these old brick Denver houses. First floor cracks. No, I don't think the roof is causing this crack, ma'am. Do you notice that your foundation is moving? Or you've got long sections of wood coming into a cove. This is all facade. There's nothing structural here. Now, roofing does cause cracks. When you're tearing off, you have a lot of vibration. You're taking a lot of load off the roof. You're putting a load back onto the roof. So that vibration can cause minor cracking. You're changing the weight in some cases. So always, always take a look at the house before you start. Take pictures of any cracks. Put a note in your contracts that say, hey, minor cracking may occur, not a structural issue, but I would say it's worth it to get to know a good drywall or paint guy just in case. Take a look, take pictures of the cracks. This is a house movement crack. It existed before the roof went on, and the reason that you see the picture is because we took a picture before the roof went on. We actually had an HOA where we went into every unit and took pictures of all the existing cracks. One person complained. We had 4 pages of cracks, pictures from his unit. We had the before and the after. There was no change. The roofing contractor was not responsible. You notice the cracks? No, those are cobwebs. And if you just wipe them with a rag, the crack goes away. This is another one where there was a large crack, but there was nothing bearing. It was all just a house shifting, not anything. It wasn't even, there was no bearing at all in this area. The other is you go and you look around the outside, you see slabs that have dropped. That all was at the same level. You can see the concrete mark on the brick wall. So when you see things like this, you have a potential that there's going to be some cracking because things are moving. That's where you take a lot of pictures because you don't want to be responsible that it wasn't your dumpster. It wasn't your loading truck. It was there, ma'am. And here's the proof. Sometimes things are not level, and it's always worth it to take a quick check. I do as an engineer, but it's sometimes if you're not sure, you know, gee, these electronic levels are, you know, $100 maybe, and you throw it on, you take a quick picture, and you move on. So, all right, that's just the quick and dirty. Mr. Roofer, I have a crack in my house. So Debbie, I think this was our next poll question. So what should you do? Verify it is one of your customers. Tell them not to worry and hang up. Compare the description of the crack with the photos you took before you started and see if it was pre-existing. So we'll go about a minute. And this time I did look at my clock, so I know how long you have. That's probably good, Deb. And yeah, I will tell you, yeah, I would, this is one I thought about having a double answer because it's always good to do number one first, verify it is a customer. And if it's not, still might be worth it to go out and look because they might become your next customer. Let's talk a little bit about condensation. This will finish out our hour. And we've got to understand some terminology. Humidity is water vapor in the air. There's 2 kinds of humidity. There's absolute humidity, and that is the amount of humidity, the amount of water measured in grains of water per pound of air. The relative humidity is the amount of humidity in the air relative to how much the air can hold. The dew point is the temperature at which the air is holding all that it can hold and water will start to condense out of the air. So the main box on either side is how much water the air could potentially hold. On the left, it is the 30% relative humidity, meaning it only is holding 30% of what it could hold. And on the right, it's 60% relative humidity, meaning it's holding about 60% of what it can hold. Hang on one second. Ike, could you leave me off? Okay, get some paper. Okay. My grandson just has to get some paper, so he's getting some paper and then he'll move on. If we have the same amount of humidity, but we lower the temperature, we change the relative humidity. So the larger box with a certain amount of water, that's 30% of the relative humidity. The smaller box, the same amount of water, it's at 50% relative humidity. If we continue to cool that mass of air down, at a certain point, the air's capacity to hold water will be reached, and that temperature is the dew point temperature. At that point, we will begin to have condensation occurring. And it will occur on the coldest surface that's available to it. So, basically, if we're going to control vapor movement, we can do this with a vapor retarder. And we used to say vapor barrier, but there's no real perfect barriers. So I have a cold temperature in my attic. I have a high vapor drive because I have a warm temperature and lots of moisture inside, and that is trying to get out. And I can block that by putting in a material that has a very low permeability. So even though there's a high pressure, only a little bit of it gets through. And that way, if there's only a little getting through, we can very quickly and easily get it out of an attic through ventilation. So advent, what to do when bathroom wallpaper starts to roll up. It's different. There's no feedback here saying nobody's laughing. Of course, nobody would have been laughing in a large group either. So we can add venting, more venting, dilute the vapor, spread it out over more air. So the colder air is drier because it can't hold as much moisture. And if I limit how much moisture gets up, I can dilute it. And then if I have ventilation low and ventilation high, there is a net convective flow, and it takes the vapor out of that attic space. And the reason that you don't need as much venting area if you have a vapor retarder is because less vapor gets through. I have less that I have to move out. Nice and neat, but the real world is you don't have enough way to get the moisture out. The moisture will condense, and that condensation will cause problems. How is this observed in the attic? Very commonly, it's observed as dark rings around nails. You have an interaction between the wood and the iron in the nails, and so you see the dark rings. You will see rust on the nails, all good signs that you have a condensation problem. So 2020, really bad. Why? 5 days of single-digit lows, 12 days with sub-freezing average temperatures. I actually had forgotten to change out this slide from the 2013. It's the same, basically the same slide. 7 years difference, same conditions. Notice the blue is precipitation. We had snow early on in February. We had cold temperatures in February. Normally in February, our daily high is above 40 degrees. The average floats right at freezing, not below it. If I have snow on the roof, and you can see we had snow on the roof through most of the month, that north face stays below freezing. As you get moisture from inside of houses, it gets to that underside, condenses on the nails, and we have a problem. This is manifest in some cases as just little leaks. You'll have a wet spot, this big or this big. Houses that have, quote unquote, never leaked have a problem, and it's all on the north side. And the reason is because we don't get the sun. We have a blanket of snow, which maintains the temperature below freezing. Then when it does melt, now all that ice that's accumulated on the nails drips in, and we have a roof leak. So, always ask, when does it leak? Oh, it never leaks in the summer. It only leaks in the winter when it thaws. That's important to know. When did it start? Oh yeah, last weekend it dripped. We haven't had precipitation in 3 weeks. Well, yeah, but it got really sunny and then it started to drip. You do a flood test or a water spray test. Nothing. How much water? Oh, just enough to stain the ceiling. Or just a little, you see these little water streaks that come down on the wall. Take a look in your attic or their attic. And what you see are these nice dark rings, dark spots around the nails. What's interesting is I've been in some roofs where you can tell that they've been re-roofed a couple times. The oldest ones had the biggest rings around them. Look at the insulation. And what you'll see are these spots. And in this case, you've got a little bit of rust in them. Not always. Basically, there was ice that formed on the nail, built up to the point that when it did release, it dripped down in. Now, it may not even be enough moisture to get to the bottom of the fiberglass, but this is a sign you have a major moisture condensation problem. This is not a good thing. We don't want to see this kind of dripping going on. So what are you seeing? The north side stays colder, holds the snow, keeps the nails colder, place for the condensation to form. So how do we tell the difference between a roof leak and a condensation problem? Well, roof leaks tend to be very localized. Basically, if I have a hole in the roof, it is a hole in the roof. It comes in one spot and going down the slope, it spreads. So we may end up with an area along a wall that has moisture coming down, but we can see inside that it's a fairly isolated location to start. On the other hand, if when I look in the attic, I see water staining all the way down large areas, that's a condensation problem. Unless you believe that you can have a whole bunch of holes over the whole roof somewhat uniformly. So the more uniform the signs of moisture, the more likely the cause is condensation. If you have a local spot with a lot of moisture and nothing else around it, very likely the cause is a leak. And now you've got an idea of where to start looking for it. So the condensation is going to be rusty nails everywhere. The wood will be discolored, and a large area is going to be affected. Now, if the area is shaped like this, starting with a single point near the ridge, okay, that starts to look like a leak. But when the whole ridge is involved and a whole, especially the north face, no, we probably have a condensation issue there. Now, there's one other situation that occurs because we say, okay, let's get rid of condensation problems. Let's increase our ventilation dramatically. Well, guess what? Then we have this problem. This is what happens when you have too much ventilation and not enough snow protection. And this is snow which blew in through the ventilation, accumulated in the center, actually above a living room, and this did this on a whole series of apartments, and it would build up through some amount of time, then melt, and it would evidence itself as water stains like this in the middle of a living room. And the owner was like, well, I don't understand why I have all of these problems in this specific type of unit. Well, all of them were the top floor, all of them were under a certain type of roof vent, and put in a vent system that had baffles, and guess what? The leak stopped. What do you know? This is not considered an acceptable way to put in ventilation. This was some homeowner's idea. When you have these leaks that you believe are condensation, first question, do you have an April air humidifier? I would say a large percentage of the complaints that I deal with, they have April air units. These are very efficient units at putting water into air. It's that they're running the humidity too high. It's not that the unit is a bad unit. It's a great unit, very good. But in the winter in Colorado, you really shouldn't have your relative humidity higher than about 30%. The controllers for these things are plastic. They're molded plastic, and they have a 30. I have seen where a person has set the unit at 30 and we're getting 50% relative humidity. My advice always is they should get their own little miniature indoor weather station to see what their humidity is. I've got one right behind me, right back here. So I have indoor relative humidity right now is at 35%, and I have a dew point of 42 degrees. That was, I don't know, 35 bucks, 40 bucks. It's amazing what you find. Now, when I go in to do tests, about 100 bucks, you can get a lab grade psychometer is what they're called, and you can check to see how high the humidity is. When you have a house that's wet, it takes a while for it to dry out. So somebody says, oh, I turned it down yesterday. Yeah, but all the furniture, all the wood, all the drywall is still holding moisture. It takes a while for that to dry out. So a lot of these are not roof leaks. You've got to find out where the moisture is coming from, whether it's a humidifier or teenagers showering or what. You've got to control the source. Adding a vapor retarder can help, but in an existing home, you might have to take the insulation out. And then there is sometimes a limit as to how much venting can be added. So, best way to reduce condensation. Use a peel and stick underlayment over the whole roof. Switch to wood shakes. Put 6 mil poly over all the insulation. Increase attic ventilation. Take about a minute. Deb, that's probably enough time. Increase attic ventilation, absolutely. You know what, I'm a little surprised I didn't have anybody say switch to wood shake, so there's no old timers around. I actually have had some situations where people switched away from wood shakes with number 30 organic felt, and they developed a moisture problem. And one of the things that we actually looked at was the fact that with a wood shake roof, you actually do get some moisture loss through the wood, through the plywood. So it's kind of an interesting one. And I threw that in there just to see if we had any real old timers with us, because that is something which I had an old timer say, "Oh yeah, you put wood shakes on a roof. You don't have to vent. You don't have to vent it because the moisture will go right out through the wood shakes." So all right, I am going to put in one shameless plug for the education programs for the Colorado Roofing Association. If you haven't sent anybody to any of the classes, we have classes that we're starting to schedule for next fall, and we are working hard to make sure that we are following all the guidelines as far as COVID goes. I have 3 litigations going right now against contractors that if they had come to class, they wouldn't be in litigation. I'm doing 2 defense projects right now for contractors who obviously came because what they did is perfectly fine. They just have some lawyer doing a shotgun. So definitely consider, if you haven't sent anybody to classes, it's a good idea, and definitely can have a benefit. The final question for the day is, what is your current role? And Deb, will let you bring that up. And
I'm working on it.
You're working on it now? Okay.
There we go.
I was putting this one in. There we go. I didn't shut off the other phone in my office, so sorry about that.
And then we have our first question to answer to.
So this will capture that and make sure everybody gets their CIUs. And I'll take a look at question. Yeah, while you're answering the poll question. Question is, have you seen issues with using a full layer of ice and water shield with condensation? Yeah, I actually have. In the mountains, we do definitely use full layer ice and water, just because of some of the icing issues. If you do that, the ventilation through other methods is absolutely crucial, because what you're doing is you're putting in ice and water shield is almost the perfect vapor barrier. Asphalt with a little bit of SBS to make it sticky is virtually impermeable to water and water vapor. So therefore, if I put that over the wood and I go into a cold environment, then what happens is, if I don't have another way to get that moisture out, it will condense on the backside of the ice and water, and you will start to see delamination and rot. We had a problem with the roof over the swimming pool at Keystone, where totally rotted out the plywood deck. And the problem was, they didn't try to keep the water vapor in the pool area. They put in these stupid lights that had a thing around the sides, so the heat from the lamp drew the moisture up into the attic, and virtually no amount of ventilation could stay ahead of it. So what ended up happening is, we sealed around those and then increased the ventilation and put mechanical ventilation with a humidistat, so that it would, as soon as it got to a certain level, a fan would bring in fresh air. Question came in about water coming in through bath exhaust vents. Actually, I've seen it where it's not actually coming in through the vent, but because they run that aluminum tube up through a cold attic, and I'm putting a lot of moisture in, what sometimes happens is that you get condensation inside the aluminum tube, and it drips back down. So you have a couple choices. One is they can be insulated. You put some insulation, that will keep the metal a little bit warmer. The other is, and I actually have seen people do this, they reverse lap them so that the water that condenses comes down, runs down the outside of the pipe, gets into the insulation, but it's not enough to matter much. And that's not an ideal way to do it, but I have seen that done. Dan Coupet, basic design speeds, its ultimate and design are the same, but with that radical 0.6 conversion factor. And absolutely, they're totally confused. That's why the V ultimate is what the code people want to see. Every report I do at this point, I always say V ultimate and put that in. Then I will put V design, and I do my calculations based on that design number. And never had a problem. But what the problem is that some of these guys don't understand it. They only know what their ultimate is. So when you're working in Boulder, those are ultimate velocities. They are not a good design number. You multiply that by 0.775, or you multiply the result by 0.6, and you get the same number. So I hope, Dan, I hope that answers that question for you. Okay, any other questions? If not, we're at 3:03, so we've kept it pretty much on time. Thank you all, and if you have individual questions, most of you, I think, probably have my number already, or you can send them an email or send it to Deb, and she'll get it to me. We'll try to make sure we get everything answered. The next webinar is that I'm going to be doing will be on the 2018 energy code and some of the things that have changed since the 2015 and the 2012. Because believe it or not, all three of them are in use right now around the state of Colorado. So thank you very much for spending an hour with me.
And thank you, Rich. We appreciate your taking the time and talking to a screen for us.